Welcome in, everybody. In this video I'm going to go over how you can graph two different types of functions here using tables. First, I'm going to start out with parabolas that are the graphs for quadratic functions. Then I'm going to move on to the square root functions. Let's get into it. For the quadratic parent function, you can see that the equation for this will be y equals x squared. And what we're going to do is we're going to use these values here for x and find the corresponding y values. So when we substitute 2 in for x here, we will get that y equals 2 squared, which is 4. So the corresponding y value here is 4. And we can do this with every other value. When you substitute 1 in for x, 1 squared is 1. So when x is 1, y is 1. And we can do this all the way down. And I might say you want to be careful when you square a negative number, you will get something positive. From here, I'm just going to plot these ordered pairs. So we have 2, comma 4, that's that point right there. 1, comma 1, I'm working my way from the bottom of this table upward. 0, 0, negative 1, 1, and negative 2, 4. Then, since this is not a linear function, this has to have a nice curve to it. So make sure when you draw this, it has a nice curve to it. So let's see if I can do this. Not bad. And this is the graph of a quadratic function. We call this a parabola. So a parabola is not the equation. We call this a quadratic equation when at the highest power of x is 2. And when you graph it, the graph has a special name. It is parabola. Let's take a look at how we can transform this graph and still preserve using this table. On this slide, we want to graph something a little bit different. It looks pretty similar to the one on the previous slide, y equals x squared. It's just that this x squared is being multiplied by 3. So here's what we can do. We can show a little work. So I'm going to start with the x value of negative 2 in the table, and I'm going to substitute that in for x, negative 2 squared. And the reason I'm doing that is because this is what we would need to figure out if we substitute negative 2 in for x here, and then y would be equal to that number. All right. So to simplify this, we need to square the negative 2 first. So negative 2 times negative 2 is a positive 4. Then we can take that positive 4 and multiply it by 3 to get a 12. And we can do this down here too. So 3 times negative 1 squared. Negative 1 times negative 1 is positive 1. Positive 1 times 3 is 3. And you can go through and find the values for these other x values that were given to you. So now we can see that negative 2 x value is paired up with a 12 y value and so on down the table. And we can do exactly what we did in the last graph and plot these points. So 2, 12, 1, 3, 0, 0, negative 1, 3, and positive 2, 12. And you can see that this graph has changed a little bit. Ooh. Try to make it as nice and curvy as you can. I'm going to come over here in a different color and show you where the graph from the last page was at. And I just want to talk about this for a few seconds. So the yellow graph here is the graph from the previous slide. And it looks as though the red graph, as you may have heard before, got narrower or thinner. And technically, yes, that's how it looks, but that's not really what's happening here. What's happening here is that the graph got taller. So you can see on the yellow graph, when we went to the right one, we only went up 1. But when we go to the right one for the red graph, it doesn't just go up 1, it goes up 3 times that amount. And when we go to the right 2, on the yellow graph from the last slide, it went up to 4. But if we go to the right 2 for the red graph, it goes all the way up to 12, 3 times that amount. And that's what's happening here. The y values got bigger by a factor of 3. On this slide, another example, but this time we changed the number from a positive 3 to a negative 2. So it's negative 2 times x squared. We're going to use the same values here for x. And what's going to happen is, again, we're just going to substitute negative 2 in for x. So from the last slide, negative 2 squared is a positive 4, but positive 4 times a negative 2 is negative 8. And we can do the calculation here. Negative 1 squared is positive 1 times negative 2 is negative 2. And again, you can go through and do all the work for this. There we go. And this is what you would get. And again, we have 5 ordered pairs. So the first ordered pair is 2 comma negative 8. So way down here. Then we have negative 1, negative 2. There we go. 0, 0. Negative 1, negative 2, and negative 2, negative 8. Go ahead and draw on your graph. Do the best you can. And I'm going to go ahead and draw in the parent function from the very first example I did. Right, so from here, here, here. There we go. All right. So this is the graph from the first example. Close enough. And what you might notice is that the graph from the very first example for the quadratic parent function has now been reflected over the x-axis. Now, why did that happen? That happened because of over here in the equation, there was a negative in front of our number. From there, you might have also noticed that it got stretched out a little bit, and that's because of this 2. So a number being multiplied to x squared will stretch the graph out a little bit, make it a little bit taller. But having a negative in addition in front of that number will reflect it over the x-axis. Let's take a look at square root functions. When you start graphing square root functions, you may want to use the same numbers I used on the previous slides. There are multiple things wrong with this. One, when you put a negative number in for x here, you'll end up with an imaginary result. And when you're graphing on a coordinate plane, there's no room for imaginary results. So we can't use negative numbers, so I'm going to go ahead and get rid of those. Bye. And another issue that you run into is that 0, that number's fine. You can take the square root of 0, you get 0. 1, also fine. You can take the square root of 1 and get 1. But when you take the square root of 2, you get 1.414. And that doesn't graph very well over here. I mean, you can go over maybe to what you think is 1.414, and that's not really going to work out very well. We want numbers that are going to be whole so we can remember them. So that means we have to get rid of 2. As I move these values up, I would like for you to think, what is the next best number that will give us a whole number for our y value? Well, 2 we said put in here, 1.4. If you put 3 in here, you get 1.7. Oh, but if you put 4 in here, you can take the square root of 4 and get 2. And we can continue this perfect square pattern here. So when you put 0 into the square root, you get 0. When you put 1 into the square root, you get 1. When you put 4 into the square root, you'll get 2. And when you put 3 into the square root, 9 into the square root, you'll get 3. So 0, 0, 1, 1, 4, 2, and 9, 3. Just go ahead and connect those as best you can. We cannot let this graph go any further left than this because you cannot put negative numbers in here for x. Again, it will give you imaginary y values, which do not exist on this coordinate plane. Now with this particular function, we will not be multiplying a number in front of the parent function. What we're going to do instead is add an extra term, just a constant term, behind it. This could actually be written in the following manner, and this is done just to confuse students. Don't let that be you. So using the values we had from the last slide, we can go ahead and figure out what the y values will be for this particular graph. So we can substitute 0 in for the square root plus 5. We know from the last slide that square root of 0 is 0, so we're just going to add 5 to it. So 0 plus 5, 5. The next value 1, the square root of 1 is 1, plus 5 will give you 6. The next one, square root of 4 plus 5, the square root of 4 is 2, plus 5 is 7. And finally, we will have 9 substituted in for x up here. And say the square root of 9 plus 5 is 3 plus 5, which is 8. Now when I plot these over here, we will have 0, 5, 1, 6, 4, 7, and 9, 8. Is that right? That looks right. Cool. And we will just draw this off to the right. Now, just to compare, the parent function for the square root looks like this. 1, 1, 2, 3, 4, 5. Oops, I missed. One moment, please. There we go. Now you can see, again, that this parent function from the previous slide changed. This is the graph of what we have here. But it looks like everything got shifted up 5 units. So let me go ahead and draw some arrows. It got shifted up 5 units. And that is exactly what happens when we start adding a constant term. The graph goes up 5 units. Now, I'm not going to do another example, but you could theoretically subtract a number instead of adding a number. And what that would do, instead of moving it up, since you're doing the opposite operation, it would move in the opposite direction. So if you had a square root of x minus 14, it would move it down 14 units, but still preserve the shape. I hope this video helps you out.